Yeah, hello folks. I'm Matt Vernacchia. James and I are software engineers at Commonwealth Fusion Systems. We're an MIT spin-out in Boston that's commercializing fusion to help power the world's transition to clean energy. And we're here to introduce cfsem, which is our recently open source library for electromagnetics calculations. So I'll start out by reviewing why we need this software for fusion, and then James will describe how we used Rust to make it fast and maintainable. So as I'm sure you're all aware, the world is in desperate need of more clean energy. And together with wind and solar, we believe that fusion can help meet this need. In addition to being safe and clean, fusion power plants will provide dispatchable power when it's needed, and they'll be able to scale up quickly and in most places without citing political or supply chain limitations. But to get to that great vision, we need to actually make it work. Fortunately, scientists have been working on fusion for over half a century now. And based on that research, tokamaks, a machine for confining a plasma, are now a proven technology that has gotten close to, but not quite achieved, net energy. We're now on the cusp of a breakthrough, however, because this past research has proven that tokamak performance scales like magnetic field to the fourth power. And we now have stronger magnets based on HTS superconductors that can allow us to confine a denser, more powerful plasma in a smaller, cheaper tokamak. We're working on building Spark, which we hope will be the first commercially relevant net fusion machine. The goal is to get to net energy, Q greater than 1 in physics terms. And to do that, we have a validated approach based on a peer-reviewed physics basis. We've demonstrated the new, stronger HTS superconducting magnet technology, and we're building it now. The Spark facility, the room where our tokamak is going to go, is under construction in Devens, Massachusetts. And behind it, we have our superconducting magnet factory, where we have 3 production lines running, building magnets with this new HTS superconductor technology. Within our tokamaks, electromagnetic coils will create powerful magnetic fields of about 20 Tesla by flowing large currents of tens of thousands of amps through superconducting cables. And to calculate all of the complex magnetic and inductive interactions that are sketched out on this slide, we need good electromagnetic software. So on the next slide, I'll get into a toy example of how that software works. For this toy example, we're going to calculate the magnetic field from something called a Helmholtz coil pair. That's shown in the bottom left of the slide here. It's a pair of circular coils that produce a region of nearly uniform magnetic field between them. So turning to the code, we start out by importing the Python bindings for cfsem. Those are made with Pyo3. Like Fabian said earlier, we too love Pyo3, great library. Then there's some omitted code here where we would define 2 current filaments, one for each coil of the Helmholtz coil pair. And then we define NumPy arrays of the R and Z points at which we want to evaluate the magnetic field using mesh grid. Then we call flux density circular filament. This executes calculations in Rust to evaluate something called the Biot-Savart law that calculates the magnetic field at each point. And it evaluates those calculations much faster than we could in Python, even using NumPy. This returns for the magnetic field B vector, its radial and axial components at each evaluation point. And those are then plotted on this magnetic field map below. And we see highlighted in red here the region of nearly uniform magnetic field that we're looking for from this Helmholtz coil pair. So now I'll turn it over to James, who will talk about how this all works under the hood.
All right, now for the what and the why. So filament calculations are essentially hand calc shortcuts to solutions to PDEs that you might otherwise use finite element or boundary element or fast multipole to solve. The short answer to why would we do this is it's much, much faster and much simpler to set up the problem if it works for the problem at all. The filament calculations, they're basically a way to relate the solution of the PDE at a point to a source term at a point. And so the solution becomes less accurate as you approach the source points, but it rapidly becomes nearly exact as you get more than a few centimeters away from source points. So as long as you know where the current is going to go before you start your solve, you actually can get really accurate results out of this, like well sub percent. Fortunately, when you're working with superconductors where copper is an insulator by comparison, you have a pretty good idea of where the current is going to go before you start your solve, which is great. It doesn't work for everything. If you're trying to, for example, ask a question about where the current does go, then you may need something like finite element instead. So there's sort of a triage of looking at what type of problem you're trying to solve and figuring out which method will be appropriate. Next slide, please. Yeah, as far as why we ended up settling on Rust for this, the usual pattern for taking a dense compute task prototyped in Python would be to, then go to GPUs. It's, dense array operations bordering on embarrassingly parallel. That actually was my first stop, was an OpenCL implementation. But really we have two priorities for this, which is barrier to entry and then performance in that order. And within the company, because this is used to make internal engineering tools, we have maybe 2 or 3 people who are comfortable setting up and maintaining a GPU computing environment. And 20 or so users who would not be comfortable doing that. And it's a significant improvement both in our productivity and quality of life for those people to have those extra 20 people able to use the tools. Because that means people don't need to be getting, calls at night and on weekends for things that they can do that their coworkers cannot. And even if we're just looking at performance, the methods in here, the relatively performance sensitive ones that we've pushed back to Rust, are actually quite a bit faster than the OpenCL GPU targeting methods that they replaced and took less time to develop. And really, that's just a matter of getting the barriers out of the way of the compiler and the CPU and cache controller and whatnot to do what they do best. Really that comes down to avoiding allocation and making sure to optimize branches out of your hot loops and just operate on dense slices whenever possible. And you can get a lot more out of a CPU core than you would expect. We've been seeing 10 to 100x speedups of these calculations compared to NumPy implementations, and still several times speedups compared to JITs like Numba and stuff like that. So next slide, please. As far as the project structure, we publish both a Rust crate, which has everything that we have taken the time to rewrite in Rust so far, and also a Python package, which has everything that's in the Rust crate via bindings, and also some additional calculations that are either less performance sensitive or are sort of at a prototype stage and haven't been optimized for performance yet. And they're split into 2 repos for no other reason than that lets us use off-the-shelf CI workflows. So the Rust part is published using the release please and cargo semver checks workflow, which gives us some automated procedural semver linting, which really helps keep the surprise breakage in downstream uses low. So that's been a really great guarantee to be able to provide that the version actually means something, and we won't be.
Sorry, James, you're at time, so could you briefly summarize?
Anyway, all this comes down to a one-line build in the end for both the Rust part and the Python part. just pip install or cargo build. And when you're thinking about whether to rewrite something for performance, just make sure to think about what you would do with it that you're not doing if it were faster, not just how much it would pay for itself in terms of your current workflows. Thanks.
Awesome. Thank you very much. Are there any questions for Matt and James in the chat? Check the Q&A. Okay, I have a quick question. There's a question from the audience. Okay, Adam says, how much time does the typical operation take? I'm not sure exactly what you mean, but maybe
yeah, I think I know what you mean. So like that example, doing the solution takes under a millisecond, and the plotting actually takes much longer than doing that solve. So for like simulations that run some kind of iterative solver and use those underlying calcs, you'll usually see like run for record, like full physical, like reproducing a test kind of resolution run in 10 to 100 milliseconds. And that usually lines up when we do finite element equivalent solves, just to cross-verify stuff and whatnot. Those will typically run in like 5 minutes or so for an equivalent solution, and sometimes as much as several hours. And that's it's big in terms of our ability to hand these tools to people to use on their laptop to do the both design analysis and day-to-day operations.